welcome to Chemical Engineering Thermodynamics 2 class. So this is our day 3 class. Again the same unit, refrigeration, unit 5. We are going to see the two more topics which we left in the last class. That is, before going to the topic, I'm going to start with the one more important part the question in this unit. That is the choice of refrigerant. It is one of the very repeated question in this unit. Okay, we frequently use Freon 12 as our refrigerant because since it is non-toxic, non-flammable and non-explosive, it doesn't have any bad effects. So that is the frequently used refrigerant. Other than that, we'll be using a methyl chloride, carbon dioxide, sulfur dioxide, propane and ammonia also. That is also a frequently used refrigerant, but when it is comparing with Freon 12, it is less used. Okay, now these are the different refrigerants we'll be using. So when you choose the refrigerant, what are the characteristics to be considered? So that is what this question is. So these are the different parameters or characteristics to be considered when you use when you use a particular component as the refrigerant. So first one is the boiling temperature. So this boiling temperature should be less than your desired temperature. Okay, so it should be less than the desired temperature. Your temperature should be lesser than your desired temperature means you have to choose the pressure which will be greater than the atmospheric pressure. So that is the data about the boiling temperature. Then is freezing point. Your freezing point should be you have to maintain the temperature that should be higher than the freezing point. Then you can avoid this freezing when you're doing the process. Okay, so that is about the freezing point. And next is your critical temperature and pressure. Okay, when you consider this critical pressure and temperature, your pressure, that is operating temperature and operating pressure, should be less than your critical pressure and temperature. If it is greater than your operating temperature and pressure, it will be impossible to condense the gases. So that is about this point. And next is condenser and evaporator pressure. Condenser and evaporator pressure should be very high in order to maintain this process. Okay, it should be very high. And specific volume. Next one is specific volume. Your specific volume determines the size of the compressor. So it depends on which type of compressor you're using. We have two types of compressor. One is reciprocating compressor and other one is centrifugal compressor. When you're going for reciprocating compressor, it should be less. Your specific volume should be less. And if you're using the centrifugal compressor, your specific volume should be high. So this is about the specific volume. And the next one is latent heat. It should be very high for the good refrigerant. Okay, so this is about this. And next one is specific heat of the liquid. It should be low. Your latent heat and specific heat is inversely proportional to each other. And the next one is molecular weight, which is directly proportional to your specific volume. Okay, so again same, if you're using your I told there is a two types of compressor. One is your centrifugal compressor and another one is the reciprocating compressor. So based on the compressor you can consider the molecular weight of the refrigerant. Okay, and next is safety aspects. Of course, it should not be corrosive, it should not be non-toxic, it should be non-flammable, it should be non-explosive, etc. So these are the safety aspects you have to be considered when you choose your refrigerant. And other aspects is nothing but it should be available for the long period. So that is about the choice of refrigerant. These are the parameters to be considered when you choose your refrigerant. Okay. So next one is nothing but the next topic is nothing but the air refrigeration cycle. Okay. So air refrigeration cycle. This is one cycle. Here it will be using only one phase. That is air is the only phase or gas is the only phase. There won't be any liquid phase. It is a single phase refrigeration cycle. That is one of the very important parameter here. Okay, we are having two things. One is cooler and other one is the heat exchanger or evaporator. This is cooler and this is the heat exchanger or evaporator. And again, you'll be having your compressor and the throttling process. Here, these two processes, that is cooler and the condenser, cooler and the evaporator will be a adiabatic process. Okay, here it will be completely a single phase gas. First, you will be sending your gas, which will be compressed completely, Then it will be sent to the cooler. From cooler, it is sending to the throttling process. Here the pressure is increased, and then it is to the evaporation process or refrigeration process. Again, it is sending to the compressor. It is a cyclic process. This is your throttling process and the compressor. Here your pressure is varying, but in this two process your pressure is constant. Okay, so this is about the air refrigeration process. You can see the animation of the air refrigeration process. You can see the line diagram here. You can see this here. So one is refrigeration. Here you'll be having the air which is sent to the compressor. Here your pressure is increasing. Here you can see this and it is a constant entropy process. From here it is sending to the cooler. Here the temperature is decreasing and entropy is also decreasing. From there, it is going to be expansion engine. I told it is a throttling process. So, in some part, you'll be having it is an expansion engine also. In the animation, you have seen the throttling process, but in the line diagram, it is given as the expansion engine. Okay, so from this, here your pressure is increased and the temperature is decreased, and it is a constant entropy process. So from it, the output of this will be going to the refrigerator. Okay, here the temperature is increased and entropy is also increased. Again, it is a cyclic process. So this is the general air refrigeration cycle. Okay, now we'll see the equations for this. So first, you can see here the heat absorption is taking place. Here the heat rejection is taking place. So heat absorption is Q2, heat rejection is Q1. So these two equations you can see here. Heat absorption Q2 will be equal to mCp Ta minus Tb. Heat rejection is nothing but this Tb minus Tc. Okay, so that is what is the Tb minus Tc. Okay, so next is work. Work will be equal to Q1 minus Q2. So you are just subtracting these things, and my coefficient of performance will be equal to Q2 by Q1. That is Ta minus Tb. FCP will be getting cancelled, so the remaining terms will be there in the equation. Since it is adiabatic process, that is two process, both your compression and expansion is adiabatic process. So Tb by Ta will be equal to T1 by T2 whole power mu minus 1 by mu Tc minus Tb. Okay, if I take this term to the next side, that is Tb minus Tc by Tb, Ta minus Td, if I rewriting that equation, I'll be getting this equation. Once I substitute this Tb minus Tc in COP equation, I'll be getting a COP in terms of T1 and T2. So that again can be written in terms of Ta by Tb minus Ta. So this is my final COP equation for air refrigeration cycle. This mu is nothing but the ratio of the specific heat which will be given in your program. Okay, so this is about the equation for air refrigeration cycle. Okay, now we'll move to the next process, that is liquefaction process. It is one of the very important process since it will be very difficult to transport or handle or store the gas product rather than the liquid product. So it is easy when you liquefy your gas. It will be easy for you to store, transport and handle those things. Okay, so if you see in your liquefaction of gases, we have a three important methods, that is vaporization of liquid, Joule-Thomson expansion, and expansion of gases in the engine, delivering the external work. So this vaporization of liquid is a very rare process. This Joule-Thomson expansion is nothing but your Linde process. Expansion is nothing but your Claude process. So these two are very important processes which we'll be using in the next thing. Okay, this vaporization of liquid is nothing but you'll be having a mixture of things. In that mixture, the low the liquid which is having the lowest boiling point will reject the heat to the next level of boiling point of liquid. For example, one is having the boiling point of 50 degrees Celsius, the other one is having 60, and the other one is having 70. So three liquids we are having. So one with the lower lower boiling point will reject the heat to the next level of liquid, that is to the 60-degree liquid, and the next 60-degree liquid will reject the heat to the 70-degree liquid, and the 70-degree liquid will reject the heat to the environment so that the condensation will take place. So it will be converted to a liquid. So like this, the process will be taking place in the vaporization of the liquid. Now we'll see the Linde liquefaction process. This is the general liquefaction process. So first here air is your input. That air is converted into a liquid. So you are giving the air, and here the compression is taking place. Compression is nothing but the temperature is also increasing, and it is pressure is also increasing. Okay, then it is sending to the cooler. So the compressed air is cooled down here, then it is sending to the expansion. Okay, here the expansion is taking place. It may be a throttling process, it may be an expansion process. If you see in your Linde process, it is a throttling process, that is isoenthalpic process. And if you see the Claude process, it is the isoentropic process where expansion turbine will be used. So this will be different for your Claude process or your Linde process. So this process decides whether it is a Claude process or Linde process. Okay, then it will be sent to the liquefier. Here you will be getting your liquid nitrogen. Okay, this process is explained to the oxygen liquefaction. Okay, so this is the animation picture of the liquefaction process. Now we'll see the line diagram. So first we'll start with the Linde process. This is nothing but your free expansion process or isoenthalpic process. Here you can see your throttling process. It is the isoenthalpic process. That is, enthalpy is constant over here. Again, you can see the same thing. Air is sent to the compressor. From the compressor, it is sent to the cooler. Here you have the heat exchanger. Okay, this is additional heat exchanger process. Then throttling process. Again, here your liquid is separated. The part of the thing is not liquefied, so that is again sent to the reverse process. So the unseparated, unliquefied gases again is sent as the recycling process. So if you take, it is a isoenthalpic process. So I'm taking HC. So HC will be equal to, here F X is nothing but the fraction of gases liquefied. So the fraction of gases liquefied with respect to HF, and the remaining, that is unliquefied gases, is sent back to the A. So 1 minus XA represents the unliquefied gases, that is 1 minus XA X into HA. Okay, so this part is a